Welcome back to Bits and Pieces, lecture number 2, bit operators. So before the break we took a look on a few of the bit operators, the AND one, the OR one and the XOR one, and we saw how we could use them when we modified individual bits. Well, like I said before, we had some things left. We had the 4th bit operator and we also had something called bit shifts. So, well, let's start with that 4th bit operator. And what the 4th one is, it's actually something we have with the logical operators as well. It's the NOT one, the one that we in logic then we use NOT, for instance, not true, like that, to get false. But that's not what we're going to do now. So I'm just going to define a byte here, and we only need one actually. 0B and 123011101, like so. And then I want to get a result. And when you invert things, when it comes to bits, then you do it like that. And then we add the B there. So now we invert the byte there, the value there, and then we can just print it all out in the end. Print line, and then I just do integer dot to binary string, and just give it a result like that. Okay, so now if we hit compiler here and run it, we should get a result, and now we can take a closer look at what's going to happen here. So I get this result here. I'm going to add it there, 5 bits, so let's add 3 zeros. And the NOT one is fairly simple. If we had a 1, it turns into a 0. If we had a 0, it turns into a 1. Like that. So we just invert every single bit like so. We don't care about how the bits are located or anything, we just invert them. So all the 1s turns into 0s and all the 0s turns into 1s, like so. So that's pretty much everything we have for the NOT one. It's fairly simple, but we can use that combined with a few other things to actually do things here that we want to do. That was a very weird description, but actually we want to do some more things here in the person class, and we can use the NOT one for helping us out there. For instance, we have something called turn boring. We have nothing that is called like have fun, so to set it back to 0, because we have no way of setting that to 0. How would we even do that? And you might have guessed we're going to use the NOT one to do so, but we're also going to use the AND one, so we're going to use a combination of a few different operators here and see how they can work together. So have fun. Okay, so what do I want here? Well, I want the following. I want to compare it with this thing here. Obviously, this is defining the position. Okay, so what do I want to do there? Well, if you think about it, what we want to do is remove everything that has a 1 here. But that doesn't really work, does it? That would be like, well, if we have a 1, then don't do anything, and you know, that's not what we want. But what we can do is just invert the whole thing. And now we will get 1s all over the place and a 0 there, okay? And then we can use that one, because now we can use that as a mask for and use that. So, well, where we have a 1 we will keep the data, where we have a 0 we don't. Okay? That's exactly what we do here. We just want to get the data at that specific location. But if we invert everything, what we want to do now is get the data everywhere but that location, because now we have a 0 there, and then what we can do is data and equals to the inverted version, like so. So what we have now is, if we add a semicolon there, is that we get the inversion here, and then we do an AND, which makes sure that we keep all the data where we have 1s, which will be everywhere but this location here, just because we inverted the whole thing. Of course, we could remove that and just invert it manually. So 1, 2, 3, 4, 5, 6, 0, 1, like so. That would do the same thing. However, maybe we have this sequence here stored somewhere, defining where we should refer to when we want to know about if it's boring or not. Then it's much easier to just refer to that one and reverse it. And we will also see another example later on where we're going to use this as well, where it might be tricky to just do it manually. If we want to do everything manually, then we could, well, just ignore programming after all. So there we go. That should reverse this mask here, so we get the inverted version, and then we can use that to remove the bit at this location, which is going to make sure that it turns to 0 again. So I'm just going to try that out here. We don't need this part anymore. So what we can do is, for instance, do bob.haveFun like so, and then bob.printinfo. So now it should be set back to having fun again. It should be at boring there. Let's run this here. Like so. So all of a sudden this person is a fun adult with a score of 3, so we just set it back to be fun there just by setting the bit back to 0, by basically keeping everything, or well, letting everything through but that bit. So even if we had the one there, it would be removed, because the mask here is going to be 111 111 01 in the end after we have inverted that one. And we can use that for setting the score as well. As you have seen, we haven't done anything for setting the score, and the reason is the following. What if we had a score of 011 to start with, I'm just talking about these 3 here. What if we had that and wanted to set, and that's by the way 4, and then we wanted to change the score. Alright, you lost some points maybe, and we want to set it to 3. Well, then we set it to 0 1 1, and then if we would have used something like this, then these would actually just have been merged to 111. So instead of actually decreasing it, we would increase it and set it to 7 instead. So that's not what we want. So what we will have to do is remove the old score and then add a new score. Public void set score. I'm just going to use an int here, so we don't have to bother about converting it to a byte all the time. So int value, I don't know, like that, and then we can simply use that. So first of all, we want to remove the old score. How do we do that? Well, we do the same thing like we just did. So and equals to not, and then we give it this 0b123 123 12 like that. So that's the same as we use here when we get a score. So that is going to invert everything, so we get 1s at the other positions, but we get 0s here, and that's going to mean that when we do an AND here with the data, we're going to lose that data. Well, basically set it to 0, so we don't really lose it. We've told the code to remove it by doing this little neat trick there. So and equals to not, and then the mask. And now when it's empty there, we just have 0s. Then we can just do data or equals to, and then add the score there. But we divide it by 4, and we do that for a reason, because it's too far up here, but we want to move it up there as well. So I will have to take the value and multiply it by 4 to get it to that position. And like I said, when we divide it by 4, this is not actually the proper way of doing it. We can do it in a better way, but we'll see that very soon. We have one more thing to discuss in this lecture, and that's bit shift, so you might guess that that's exactly what we're going to use here later on. But like I said, that's later on. Okay, value times 4, good. But that's not enough, actually, because we haven't made sure that the value here is actually just taking up these 3 bits. So what I'm going to do is simply grab this mask here and do an AND there. So we make sure that if we have something that is outside here, it's going to be removed. Okay, so we won't get any invalid values. We'll take a look on that when we run this as part of the example. Right, so what we want to do now is head over to the bit operators test here, and then we can just do, I don't know, bob.set score, and then set the score to 5, for instance, and then bob.not have fun, print info, like so. So now we run the code, first compile it, and then run it, like so. Okay, so what we have now is this person is fun adult with a score of 3. This person is a fun adult with a score of 5. So we just reset that and set it properly. So 5 would take up these bits, 1 0 1, and the old score would have taken up 0 1 1. So if we just would merge them, we would get 7, and we can take a look on that. So if we didn't reset the old score there and just added a new one on top, then we would get an issue, and that issue can be shown right now. So when I set it to 5, we will actually get a score of 7, just because, well, we got 2 of the bits from there and 2 of the bits of there. They overlapped in 1 bit, but what we actually had was all 3 bits, and that's going to look like 7 there, like that. But what we want to do now is actually have that code to make sure that we clean up the old data and then add the new things there. And we always refer to these 3 bits because that's where we're working. The ×4 there is of course because we have the 2 zeros there. So what's the next thing we want to do? Well, I want to show you why we have this thing here. So if I set it to 8, that's an invalid value, right? We can actually set it to 9, like so. So what is 9? Well, let's run this and see the result. The score is actually set to 1, and that's exactly what we want it to be, because you added something that was too big. 9 is 1 there for the 8, and then 0, 0, and then 1 for the 1 part there. And we only want these 3. Okay. The reason why we only want these 3 are because, well, we only have room for 3 bits. That's what the location we've allocated. We just have room for 3 bits. That's the only thing we can do. And therefore we remove this data. Well, unfortunately, you said 9 and wanted the score to be 9, but that's invalid. This bit, we'll have to do something with it, just remove it, and therefore we get 0, 0, 1, and that's the 1 there. However, if we don't do that, if we don't do this part here, we'll have some weird results. We run it here. The score is still 1, but now we're all of a sudden ready for action. Right. So what's up with that? Well, remember, a 9 is 0, 1, 1, 0, not 0, 1, 1, 1, 1, 0, 0, 0, like so. So like that. So oh, 9. Derp. So this is going to be the number we're using. We're still just getting those numbers here, using that 1, 1, 1 there. So we're just going to bother about those, but we're still going to apply this 1, and that's going to go there. And if we scroll down to is ready, that's exactly what we're using here. So we're using that 1 there to get if it's ready or not. So what we're doing is applying these bits 0, 0, 1 as the score, and then we're applying this bit here as if it's ready or not, and that's not what we want to do. So here all of a sudden we're messing it all up because the user or the coder or whatnot gave it a value that wasn't a valid one, and therefore it sort of overflowed into the next data, and we got into troubles. So what we want to do is simply do it this way here, so we make sure that we only get the data in these bits here, and if the user or the coder gave us something in the other ones, then we can't really do too much about it. We will just ignore those, and that's why 9 turns into 1, but it would turn into 1 anyways because we just read those 3 bits. But it also makes sure that we won't set the ready state to true just because we happen to have a bit there that it's overflowing like that. Score of 1. Nice! So now we're going to talk about bit shifts. What are those things? Well, let's see. Okay, so I'm going to have a byte here, which is going to be 0, 0, 0, 1, 0, 1, 1, 0, like so. Right. What's the next step? Well, we want to get a result. And like always, we do it like this. Byte, if I can spell. And here's the bit shift. We have B, then we have those there, and then we have a 2. The 2 is of course optional, it doesn't have to be 2. And what we have here is the value, and then we have something called a left shift. The arrows, well, that sort of turns into arrows, I guess, are facing left, therefore this is a left shift. And then we have a 2 there. We'll take a closer look on exactly what's going on when we can take a look at the result. So integer dot to binary string, and then we use the result like that. Oops. To binary string. I can't spell. There you go. Okay, so then we get this result here, and then we can just copy that in here and do the normal comparison. What do we have? We have 3, we have 7, therefore I'm going to add a 0 there. Okay, so what just happened? Well, we did a left shift by 2. That basically means that, take a look on this. We have a 1, 0, 1, 1 there. Now we have the 1, 0, 1, 1 over there. 2 steps to the left. It's not a coincidence. Obviously, a left shift by 2 means that we're going to move every single bit 2 steps to the left. So all the zeros, all the ones we moved 2 steps to the left. All the data we had on this end here, the zeros there, well, are going to be removed, and then we add zeros here at the bottom. So we just added 2 extra zeros there. We can take a look on that. If I add 1 there, we're not going to see that this one gets back or anything. It's just going to be get removed, and then we get zeros there at the very bottom, like that. So we still have the same result here. It's the exact same that I just had, because this one is just going to be shifted 2 steps to the left and therefore get removed. It's going outside of our bounds there, and then we always refill with zeros there, like so. Let's remove that for now. Okay, so that was left shift. Quite simple. What do we want to do with a right shift? Well, just invert the direction there, hit compile and run. Done. And the right shift is going to give us 101 there, so that's a very short one. Let's add zeros. 1, 2, 3, 4, 5, like so. So as you can see, we have moved these 3 there 2 steps to the right, and these 2 here are being moved so far out that they are, well, removed completely. They are shifted outside of the actual value, and therefore we lose that information, and we just refilled with zeros here, like that. Right, so how can we use these things? Well, these are the missing pieces in the person class here. These things here. Of course, I can divide it by 4, but what I'm actually doing is just dividing it by 2 each time I want to shift it to the right. Okay, so what I can just do is shift it to the right 2 steps. It was very easy to just divide it by 4 right now, yes, because it was only 2 steps. But if it's like 17 steps, what are you supposed to divide it with? Well, 2 to the power of 17. What's that? I don't know. Just shift it to the right 17 steps. So like that. So now when we get the result here, it's going to be shifted down 2 steps, and therefore we're going to get a result at the very bottom there. But we of course have the data like so. So everything is just shifted down, and that's the result like that. Sweet. And then we can do the same thing here. We want to do the value, and we want to shift it up to its proper position, and we multiply by 4 each time we want it to move upwards. And what we can do instead is just to of course shift it by 2. And as we saw here, we could do it with multiplication and division instead, but in some other cases it's much easier if we can actually just shift it by tell it to shift, rather than, alright, what does it mean when we shift it? Alright, if we multiply with 2, it's going to give us the same result as shifting. So in the end, when you multiply by 2, what we actually do is to shift all the bits 1 step up. And that's the same. It's no difference when we work with base 10, because obviously what base 10 is, it has the binary, the bits there back end. So when we want to multiply that with 2, what we do is just shift all the bits up, and then it converts that binary to base 10 again. So nice. Before we go on to a final example, I want to show you one last thing with bit shifts, because we actually have 3 bit shifts, and we don't have like left, right, and up or anything like that, but we have another version of the bit shift here. I'm just going to remove these things here, and to show that I can't actually work with bytes anymore. I will teach you why in just a second, but I want to work with an integer here. Row B 1, 2, 3, 4, 5, 6, 7, 8, like that. So that would be a normal byte, but because I'm lazy, I'm just going to copy that 4 times, or well, copy it once and paste it 3 times. So this is just a 32 bit long sequence, because we now have an integer rather than a byte there. And I will show you in just a second why I have to do it like that to show this example. So int result equals I, and I shift that 2 times to the right, and then what I want to do is print this out. System.out.println integer.to binary string. Binary string, like so. Okay, I'm going to hit compile, and we can see nothing special really. But what we get here in the end is we can take a look at the end, only like 0, 1, 0, 1, 0, 1, like so, and those are those there. Ones. Why do I say zeros for ones? 1, 0, 1, 0, 1, and that's well, this part there. like that. So it seems to be working. We just shift everything 2 steps to the right, like that. But you know, nothing new. But what we can do is the following. Result 2 equals I move through. There's something weird with the result we just got. I don't know if you noticed. I didn't speak about it, so distraction. Integer dot to binary string result 2. So as you can see, I've used a triple version instead of a double version there, and that's the third one I was talking about. There's one left shift. You can always just have the double there when you left shift, but when you do a right shift, you can either do it with 2 greater than or with 3, which is going to do slightly different. That's why I'm printing out both of these here. To binary string, I don't know what that would be. To binary string, there we go. Let's compile and run this like so. So now we get 2 sequences here, and one seems to be a bit shorter. The only reason why this is a bit shorter is because it happens to have 2 zeros here at the start. So what we can do is copy these guys up here and just align them properly. So what I'm going to do is just comment them out there. Like so, and then I'm just going to add 2 zeros there. Okay, so if we take a look on these sequences, it's easier now when we have these zeros added there. We can see that they are pretty much the same here. 1 0 1 0 1, yeah, and so on. It's the same. Both of these are the same, because what we do is shift it 2 times to the right both of the times. However, take a look at the start. We have a 1 1 and we have a 0 0. What's the difference there? Well, obviously the 1 1 and the 0 0. But why do we get it? Well, when we do this right shift here, the number that we do get at the top depends on the signed bit. So the signed bit is the most significant bit there, and is, like we've seen before, defining if it's negative or not, because it's worth negative its normal value rather than a positive one. And if that one is a 1, when we do a normal shift here, then what's going to happen is that we refill it with 1s at the top. So these 1s here are just being added like so, just because, well, we had a 1 as the most significant bit, and therefore we just refill it with 1s, so the result here is going to stay negative, like so. But if we have a 0 here at the top, like so, we will see that we add zeros here in the beginning, like so. So this version, the double one, there we will always get the we'll refill it from the top depending on the signed bit. So if the signed bit is 1, we refill with 1s. If the signed bit is 0, we refill it with zeros. And the other version, however, if we use that one, we make sure to always refill it with zeros. We can't get any 1s there. We always get zeros no matter what, and that's the triple version there if we want to make sure to always get the zeros at the top there. However, like I said, there's nothing like that. That doesn't exist, because we will always get zeros when we do the left shift, because there's no signed bit over here. That wouldn't make any sense. So we will always refill it with zeros from that end, no matter what, and that's why we can just do it like that anyways. I'm not entirely sure exactly why you would want to refill it with 1s, but if you want to keep it as a negative number and just add the 1s there depending on the sign there, it's quite a good way of doing it. You just use the double one here, or otherwise you use the triple one to get the zeros. However, why did I use integers? Why not bytes? Well, like I said, when we work with bit shifts and bit, I don't know if I said that, but I said that it was like that when we work with bit operators. It's actually going to work with integers. So if we have 2 bytes, it's going to treat them as integers and do the bit shift, and then we want to convert it back. And that was the same for the bit shifts. So when we take 2 bytes, if we have the most significant bit being 1, that would normally be the signed one. But since we treat them as integers when we do the shift, they will have 24 zeros before that signed one, because, well, the byte would just be these 8. I think that's 8. 2, 4, yeah, that's 8. So we would have these 24 bits being zeros, just because we treated the bytes as integers, and therefore, well, we would never have a 1 as the the signed one, and it's only when we have a 1 as the signed bit that it's going to be a difference between having these 2 there and these 3 there. In many cases it doesn't really matter which one you use, and in those cases I personally usually use the 2 1 there, because, well, the left one is always 2 like so. But if it matters, then we of course need to pick that one if we want to add the signed bit as the top one, or this one if we always want zeros to be refilled at the most significant bits like so. So we're not actually going to use this too much in the example, but this is good to know, because otherwise you might get weird results. You're expecting zeros, here you get ones, but maybe you want zeros, then use the other one like that. Okay, sweet. So now we're going to do that example that I was talking about, and that's going to be quite similar to this person one here, but we're going to see how we can in a nice way match them all together in a good way. And in the next lecture we will cover more examples even further. So next lecture we'll talk about how we can implement these bit operators and bit shifts into Minecraft and do it properly there. I've actually referred to this course a few times in earlier courses that, alright, we can't do it properly yet, we'll do that later, and that is going to be the next lecture, but we're going to have a small example still right now, and that's going to be public class compact boolean. So it's not going to be advanced or anything, it's going to be a bit similar to the person one, but here we go. Private byte data. So we're going to store 8 different boolean values in this compact boolean thingy, and it's going to just take 1 byte, and we'll see how we can efficiently just use bit shifts and all the bit operators to do this properly. Like so. We want the get flag. I'm just going to write the methods first. We want the set flag, and we want to set it a specific ID with a specific value. Then we want a flip flag. If we just want to change it, void flip flag, like that, at a specific ID. And then we want to do well, I want to have a way to get all the data, because maybe we want to you know, synchronize all this information, save all this information to a file or something like that. Then we don't want to get the individual bytes or the individual bits with the boolean, sorry, we want to get the actual byte. We want to get the individual bytes for each of these compact boolean sets, and therefore we want to return the data. And in the same way, we might want to synchronize it and load it again, and then it might be a good idea to actually load the byte that we have the data there. So byte data, like so. Base.data equals data. And finally, it also might be a good idea to be able to do the following: print debug info. So we just check which values that we have currently set, which is a good idea to do when we want to debug and see what informations we have. So just a loop here: for int I equals 0, I is less than 8, I plus plus, like that. And then it's just a matter of printing it all out. So let's do it like this one. Get flag. Okay, so we haven't defined yet how we get the flag, but of course we can refer to it anyways. So what I want to do now is define these 3 things, and to do so we're going to use a combination of bit operators and bit shifts, exactly like I described. So how do we get the flag at a specific ID? Well, we've seen before how we get a boolean with a specific mask here. For instance, we can get the boring one by checking if the one at this specific location is not equals to 0, like that. That's totally possible. But we don't have this. We just have an ID. But we can generate something that looks like that with a bit shift. Think about it. What we want is a 1 at a specific location. We have that specific location, and we know how a 1 looks like. We can just do 1 and move it up d times the ID is set. So if we have position 0, we don't want to move it up at all. If we have position 1, we move it up 1 step, and so on. So we're just going to generate something that looks like this. That would be position 1. That would be position 0. So just going to move that up there. But we obviously don't want only that. But what we want here is data and that, like so. But we also want to make sure that this is actually if that bit is set or not. So what we can do is simply check if that's not equal to 0 and just return that like that. So what we're doing, we're sort of generating a mask to use in the AND thing here, and what we get is a bit if that bit is set at this specific location, or rather the ID's location, and then we can check if that's 0 or not. I haven't added semicolon there for a reason, because if we wanted to, I'm not going to, but we could do this differently, because when we get the data there, then what we can do is just move it down again like that, and then check if that's equals to 1. So as you can see, if we actually wanted to get a 1 or not, we could just move it down again. And this is very useful if we're not looking for a Boolean value. Maybe we were looking for 3 or maybe 4 bits. Yeah, maybe 4 bits that represent a number. Maybe a number between 0 and 15, because that's 4 bits. Then what we would have to do would be move up to get the data, move down again, and then return that data like so. So if we wanted to get a number at this ID, then we would move up, but then we of course wouldn't move one up there. Then what we would move up would be 1 1 1 1. So that's what we can get from 4 bits like so. We move that up a specific location, get the data by doing AND here, and then move it all back down again before we return it. And if we worked with integers or something bigger than that, then we would have to be careful of would be that, alright, maybe we get a 1 as the top one. When we shift it down, it's sort of going to follow along with those ones. So maybe what we want to do then would be a triple there. That wouldn't be necessary if we worked with bytes, because then we will always have 24 leading zeros there, so that we're not even close of having the signed one there as being 1. So we could just do it that way. But we're not working with numbers here that we want to return. So just shift 1 up there. There's no reason to shift it down to check if it's equals to 1. What we can just do right away is check that it's not equals to 0. So as you can see, we can do it more advanced if we want to work with something that is more advanced. But like I said, we're going to take quite an easy example here and then take a closer look on what we can do the next lecture. So what I'm doing here is moving the 1 up there so we can get the data at that specific ID and then return if it's not null. Not null, not 0. Right, so that's the get flag. Then I might want to set the flag. So how do we do that? Well, we can do this in just one statement, but it's not going to be that pretty, and it's in the end we're going to do the same thing as doing 2 different things here. So we can do if value, then we want to set it, otherwise we want to reset it. Like I said, we can do this in one statement, but in the end what we're going to do is reset it and then set it if the value is true. So in the end we won't do any difference, but we will put it in one statement. If you want to, you can have that as a sort of an exercise. You use some ternary operators together with quite a lot of bit shifts and bit operators to, in one single statement, set the new value depending on if the Boolean value here was set or not with the ID there. But it's fairly easy to just do it like this. So if the value is true, then we want to set it, otherwise we want to reset it. And we've seen these things before. How do we set a bit? Well, we do data or equals to, and then we just add the mask there. But we don't have that. We have to generate that, just like before. Like that. We just take a 1 and move that up to the specific location, and that's going to set that bit like that. Okay, so how do we reset it? Well, we've seen that before as well. Data and equals to 1, and then we move that up an ID like so. But that's not enough. What we also want to do is invert the whole thing. Boom. So as you can see, the bit shifts here comes very much in handy when we want to move it up. We could of course multiply it by math.power2.id. That would in the end shift it as well. in the end we would shift it, the computer would shift the bits up, so there's no reason why we would have to multiply it and calculate the power and everything when we can just tell it to shift them up right away. So we just do it like that. So take the 1, shift it up the correct amount of positions, invert it, which makes that we actually got a 0 at that location, and there we go. Of course you can't take a 0 and shift it up. There's no bits there that we can move there, then we will just have a full 0 and we won't get any ones anywhere else. So what we do is shift up the 1 at a specific location and then invert it all. So that's setting, so we set it, reset it like so, and then we want to flip it, and this is fairly simple. Data XOR equals 2, and we've seen how we get the mask properly like that. Boom, done. So as you can see, we're using a few left shifts here. We're actually not using any right shifts at the moment, but that's just how it happens to be. We saw an example of how we could use a right shift when we move it back like so. But like I said, the next lecture we'll talk more about usages of these things. But as we can see, we're using it here to get the flag, we're setting the flag and flipping the flag like that. We're also allowing the user to get the data and setting the data to be able to synchronize that or save it or whatnot. And we can print out the debug information. Okay, go here and well, let's see. We want to create a compact boolean, and I'm going to call that flags, and it's just a matter of creating a new one here, compact boolean. And we can of course have multiple flag sets there. What I want to do is flags.setFlag. So I want to set that to true, so that's the second one actually. We have flag 0 as well. Flags.setFlag5 to true, and then I want to set the flag 6 there to true as well. Debug info, so it's just a matter of printing that and running it all. And what do we get? Well, the 1 here is true, the 5 and the 6 is also true, so we managed to set them properly, or at least it looks like that. We can do some more testing here. So what I want to do is just flags.setFlag5, so that's the one we set to true. Let's set it to false again, and then we do flags.flipFlag. Let's flip the second one, so that's going to, well, that's false already, so that should be set to true. So now we should see the 5 going to false and the 2 there to be set to true. Okay, compile and run it. So now we have 0 false, we have 1 and 2 as true, but the 5 has been set to false and the 6th one is still as true there. So nothing too complex here. We've just stored 8 boolean values within 1 byte, so we're taking up 1 byte instead of 8, which is fairly good in some cases, but we're not doing too advanced things yet. But in the end, bit shifts and bit operators they are not too advanced, but if we put them together we can get more complex things. As you can see here, we're using a shift, we're using a not, and we're using an and here, all in once in a very short statement here, and we get to get the effect we want. These things with flags is a quite common thing to have, and it's quite useful. If we take a quick example on Minecraft, for instance, when we have entities, as you should know, we have something called data watches, right, to be able to synchronize information between the client and the server. And when we synchronize, we don't want to send a ton of data all the time. And also, when it comes to data watches, if you remember, we can only have 32 of those for each entity. We can't have any more. It's impossible. Just 32. That's the only thing that we can have. Why is this important? Well, in every single entity in Minecraft, it's using some flags. One of them is if it's burning or not. I think one is if it's falling or somewhat. Maybe one is if it's just got hit, or I can't really remember all the flags, but one is at least if it's burning or not. And I think there are 4 different ones. And all of these are stored within one of these data watchers. They are just put together in a way similar to what we're doing here. So all of those 4 values are using one data watcher. Why is that good? Well, first of all, we just have to synchronize this only data watcher. We don't need 4 different ones. But second of all, we're not using 4 different bytes, and therefore we still have 31 data watchers to go, because we just use one for those 4 flags. We could of course use 4 different ones for each and every one, but that would be a bit of a waste. Yes, because, well, we can store them in one. We could store even more flags in that single one, like so. And that's one example why we would want to compact these flags as this. But like I've said multiple times, we will take a closer look at Minecraft examples in the next and final lecture. So a quick summary of today's lecture right now. Right, so we started with the AND one. So we have the bitwise operator AND, and if we do it like that, then we will get a result where we get a 1 if both the bits in the values we used are 1. So if we take a look there, we have in the very end, we have a 1 in the top one and 0 in the second one, and therefore we get a 0 in the result. There we'll see the output there will output 0 0 0 1 0 1 0 0. But we also have 2 1s there, and those are 1s just because in those locations we have a 1 in both B1 and B2. Then we took a look at OR, and when we have OR, then we will get the result as 1, where at least one of the bits are 1. So we don't need both to be 1, but just one of them. And in the output there we see 0 1 1 1 0 1 1 1, and in the middle there we have a 0, and the reason why we have a 0 there is of course because there's a 0 in B1 at that location and a 0 at B2 at that location as well. And as you can see, we can use the single vertical pipe for bitwise OR there. Don't confuse it with logical OR, where we use 2 of them. Right, then we had XOR, something new that we don't have that in the logical part there. So here we will have a result where exactly one of the bits are 1. So here it's not alright to have both as 1, as you can see at the second least significant bit there. We have 1 in B1 and 1 in B2, and therefore you get a 0 as the result. Otherwise it works exactly like the OR one, so exclusive OR there. And don't confuse that with power off, because that's not how you write to the power off in Java. That's XOR. Power off is math.pow, and then you give it 2 parameters. And finally we had a NOT one written like that, and it will just convert all the 1s to 0s and all the 0s to 1s, and we saw that we could use that when we wanted to, for instance, invert a mask. Quite handy to do so. And then we had the bitwise operators here that was shifting, well, bit shifts, which are sort of bitwise operators as well. They operate on the bits, but are actually bit shifts. And what we can see here, if our bit shifted 2 to the right, then it's going to move 2 steps to the right. All the bits, all the individual bits are going to be moved 2 positions to the right, and we're going to refill it with 0s at the top. And we can do the opposite, where we shift it to the left, and therefore everything is going to move up 2 steps like so. We also saw, if we go back here, that when we shift it to the right, we have a two greater than signs, 1, and then with the triple one as well, the longer one, and that longer one is going to make sure that we always get 0s at the most significant bits. We're going to refill it with 0s, whereas this one that we use here is going to refill it with the same as the signed bit. But we're never going to have that trouble when we work with bytes, because when we do all these bit operators, then it's going to do those on integers, even though we supply it with bytes. Like so. And here we go, questions and exercises. It's the end of the lecture. So remember, we have questions and exercises. Questions to see if you've understood what this is all about, and some exercises to practice this further. Further exploration if you want to go even further than that, but that might include things you haven't been hearing here in this lecture. And in the end, we also have answers to the questions and possible solution to exercises, but nothing to the further exploration. The further explorations is something you can do yourself. Continue on there. But that's pretty much it. This has been Bits and Pieces, lecture number 2, bit operators. I've been VSWE, and I hope you enjoyed it. Next lecture, the last lecture of this course, we'll take a look at what we can do with bit operators and bit shift and so on in Minecraft, how we can use that to do some things properly there. So some more examples, some more information there, but that's next time. Goodbye.